Right. Howdy, everyone. We're the Precision Sous Vide team sponsored by Professor Nauka. And I'm Peter Luong, and my teammates are Yuliana Razo and Armando Escalera. And today we'll be going over our final demo, including each subsystems and what things we want to showcase. So to give a brief overview of what our project is, we're designing and constructing a sous vide, which is a temperature-controlled cooking appliance designed to provide a high-quality cooking experience. That is accomplished by using various precise sensors, a heating element, and a feedback loop that adjusts the temperature of the water so that the food within the vessel cooks at a constant temperature. And we're innovating on top of pre-existing sous vides on the market by utilizing a very precise RTD temperature sensor with an accuracy of 0.03 degrees Celsius, and increasing water pump flow that should provide an even more accurate cooking process. Initially, we're developing an application in conjunction that allows the user to control every aspect of the sous vide through their mobile device.
So this diagram right here shows all of our 3 different subsystems and the way we broke up our project. On the left in blue, you can see my subsystem, which will encompass the power delivery PCB and encasings and connections for all of the hardware components, which will be the water pumps, heating element, a couple of sensors. In the middle in purple, we have Armando subsystem, the controller unit. This is where the hardware and the software is interfacing using a microcontroller. So he's doing the programming of all of that. And then in the right in yellow, we have Peter's subsystem, which is the software side of the project, where he's developing an application which will give the user complete control over the appliance, and this communication with the hardware will be via Bluetooth. So for my hardware subsystem, the majority of my time went towards making a power delivery plan in order to put it on a PCB. We are powering this appliance via 120 volt AC wall socket, so from there I had to make sure I was able to supply power to the AC driven heating element, but also give DC voltage to the smaller components such as the ESP32, water level sensor, etc. So I did go ahead and go with an AC to DC power chassis, which would allow me to go from 120 volts AC to 12 volts DC. And then from there, I did choose 2 buck converters to go from 12 volts to 5 volts, as well as 3.3 volts. From there, I also am using a proportional control relay, which would allow us to control the amount of power available to the heating element, which is something that we will be controlling. I also do have like a DAC as well as some relays, which will be used to interface with the control system in order to control the signals that will either turn on, turn off, different features such as that. And what is highlighted in tan is what will be on the PCB. The power chassis as well as the proportional control relay will not be on the board, as they are chassis mounts, which will be outside in an enclosure along with the PCB. So this right here is a 2D layout of my PCB. I do have all the components that I will be using on here. I have the ESP32, the max, the DAC, op-amp, which will be used to amplify the output of this DAC. And then I do have 2 regions up here for the buck conversion to 5 volts DC. Down here is buck conversion to 3.3 volts DC. I do have these 2 relays that will control the water pumps. I do have the connectors for everything that will be going into the board, out of the board. Into the board, I do have the output from the 12 volt chassis. So 12 volts is what will be running on this board and powering it. Because of that, I did make sure to have all the trace widths the correct size in order to allow enough current to go through. And then I have connectors for the water pumps, the water level sensor, as well as an RTD relay input, which will be going from this op-amp. And then I have the 3D model of it. Like I said, these are all the connectors, all the connections. And this, as of now, is a 4.5 by 3 inch. So this is the schematic. I do have 2 sheets. This sheet is for the converters, which is pretty straightforward, but converter circuitry for 5 volts, 3.3 volts. And then over here is where all the connections are made. DAC, op-amp, relays, max, ESP32. All of this were designated by the control subsystem, Armando. He was able to tell me what pins go where, and from there I made the PCB. So one of the experiments that I wanted to do was validating that I did the calculations correctly as to how much input DC voltage was needed to output a certain amount of power available to the load. In this case, I am emulating the heating element as a blow dryer, as they are pretty similar in load. So in this case, I basically just hooked everything up, split the hot wire in this power cord to the relay as well as the blow dryer, and then I did supply DC voltage with the power supply. In the video, you will see how when I apply 5 volts, it'll go ahead and turn it on. And if I apply 1 volt, it'll go ahead and turn it off. Those were calculated via the specs and what was given from the information of this relay.
Okay. Look at that. It works.
It'll go ahead and turn it off. So the second experiment that I wanted to do for validation was making sure that the 120 volt AC to 12 volt DC power chassis did give us what we wanted. So in this case, I did hook up an AC power cord, made it the input of the board, and the output was this water pump, which is rated from 8 to 24 volts, but I did the calculations to calculate the flow rate that we were looking for. As we know, that'll give us a very good uniformity of temperature in the water, as it'll constantly be moving the water around. So we calculated that to be 12 volts. This is kind of the setup in the back. You can see this is where the connections were made, making sure everything was hazard free. Got a container, put some water in it, and in the video you'll be able to see the water pump working, as well as some food dye going in and seeing how quickly it'll dissolve in the water. So the IC chips for the bunk converters were surface mount, so unfortunately I was unable to put it on a prototype board or breadboard, but I did make sure to have enough information from the datasheets, all the specs, as well as do simulations in order to truly understand their functionality. So I did go ahead and do some output steady state, input transient, load transient, and startup, and I did go ahead and do it for both the 3.3 volt buck converter circuit as well as the 5 volt buck converter circuit. So this right here is a 3D model of what my team and I have drawn up as to what we envision our 404 and project would look like. I did take on the role on getting familiar with SolidWorks and 3D modeling in order to go ahead and manufacture something similar to this. Obviously, we do need to do more research and figure out the best way to put all of this together, as waterproofness and temperature proofness is something that's really important in this case. So here you just have the water bath container. This is about 13 gallons. An electrical box with an AC power entry module, heating element with RTD casing, as well as some spheres that are shown here. And then we would also have a water level sensor clamped on.
For the microcontroller demo today, I'll be showing the RTD reading, as well as the water level reading, and finally, I'll be showing the BLE server. So this is the RTD sensor circuit, and this is the water bath I'm using for the RTD sensor. So this water has been sitting in this ice for quite a long time, and it is in a vacuum cup, so hopefully it'll be close to temperature. And as you can see, these are some readings from the RTD sensor, and they're pretty close to 0, so that shows that it's working well. And when I take it out of the water, the values do go up, so it is working as expected. And yeah, so far it shows this RTD sensor has been proven to be pretty close to that 0.03 degrees Celsius accuracy, and it has provided accurate readings, so I like that. Now for the water level sensor, it's pretty simple, as it just has the jumper cables and this breakout board, and this the submersible part. And I still have this water cup handy, so I'll be using this. And as you can see right now, it is reading 0, which it is supposed to be doing. And so for some tests, I'll be putting my finger and my hand over the sensor just to make sure that physical objects are not triggering the signal, as we only want water to trigger the signal, just for safety concern issues. And as you can see, it works pretty well against being blocked by physical devices or physical objects. And when I put it in and show back to the screen in a bit, you'll be able to see that I marked one. But right now what I'm doing is I'm trying to get those water droplets in the sensor to see if those create false readings. As this is something that will be in the water, there could be water droplets left in the sensor, and we don't want that to create a false reading. Thankfully, it does not. So now I'll be demonstrating the BLE server. So as you can see, I just connected to the BLE, and this is just some generic attributes for indications, and then just device name appearance and those general things. And now here, the characteristics now belong to the things that we're actually going to be transmitting. So that first one is going to be the actual temperature value. And the second one that has write permission is going to be the set temperature value. So there I am trying to send that. And as you can see, it has sent it as a hex value. And this third one would be the set time value. And the last characteristic would be the water level notify / reading. And I'm just disconnecting so that you can see it on the output later. So on this terminal output, you can see the hex values that are being written, as well as the read events. And thank you for watching.
Howdy, I'm Peter Luong, and I'll be demonstrating the final demo for my software subsystem tasks. And this project includes creating an application that will work with a sous vide device. So as you can see on the screen, I have an emulator for an iPhone. As you can see, this is where I will be running the application. This application was created using React Native, which allows for development on both iOS and Android without needing to use two different teams. So for me, I'd be able to create one set of code that'd be used on both. And it's very helpful for allowing us to create a device that is applicable for everybody and does not restrict anyone based on their phone. So as you see when I enter the application, you can see that we're brought into the application. So at the bottom you can see there's a nav bar and it has 5 different menus. So for the time being, because this is a one semester thing so far, I wanted to create a minimal viable product, which is just the essential things that the user would need. So I created the user's guide. And because the application will be the main interface that the user interacts with whenever they're using the device, I wanted to include the user's guide, which will detail how to use the sous vide device so that the user can just simply download the app and not have to read through instruction manuals. There's a simple thing right here that just shows them how to use the device and how to use the application. If you move on to the sous vide section, this is the page that will check the Bluetooth status connection. So at the moment, because I'm a standalone subsystem and I haven't integrated with the microcontroller, the Bluetooth status signal is just a placeholder, and once that is connected, it will showcase the Bluetooth status. And if it is not connected, then it will prompt the user to connect to the Bluetooth using their settings page. So when we go in, we can see that we can choose between different types of food and the level of doneness. So this gives 4 options, and then for each of these, you can see that there's different levels of doneness, because obviously you would not want to eat rare pork or rare poultry. So you can see from that, you can select many options. So for example, I can select poultry and then medium, or poultry and medium rare, and it adjusts the temperature and the doneness. As you can see at the very bottom, this is just a placeholder. As I'm testing it right now, I just want to see like what the outputs I'm getting are, and just and verify that these buttons actually work, and they actually do, as you can see. So I can enter the thickness from here. So if a typical slice of poultry, like a chop, would be around 1 inch, and you can see that it has the time right there. And as you can see, for different levels of doneness, you can see that it affects the time promptly. So once you click the configure sous vide device button, there will be a countdown, and this countdown will be used to indicate to the user when they are able to finish cooking the food, or how long the food will taste for them. So that's that. And then you can see I haven't implemented that yet, but this will be implemented with an API that will be implemented that allow the user to see various recipes that they could use to cook their food with. Going on to the settings page, you can see that I have a general settings page right now, and this will be fleshed out later with more options, but for the moment you can see that the user is able to select if they would like to allow push notifications, and whether they would like to select the temperature unit. So, for example, and because the device is mainly oriented towards American audiences, because where we are at the moment, the temperature is actually set to Fahrenheit. So that is all for the moment, but in terms of integration, I will be connecting it with the microprocessor, and from then on, the application will be more fleshed out. Now I'll be moving on to the Android side of things, which, as you can see, is pretty much the same thing. I just wanted to validate that it does work on both operating systems. So you can see once I click through all the menus, you can do the same exact functionality as you would on the iOS application. Some things being a little different graphically, but for the most part, the functionality is exactly the same. Alright, moving on to the next portion of the demonstration. I wanted you to validate that the application works on a physical device so that it's not just something that you can use on an emulator. And in fact, because it's made using React Native and encompasses Android Studio, I was able to load it on top of a physical Android device. So you can see in the video, I am clicking through all the buttons and ensuring that it is in fact working. Unfortunately, at the moment, it's not able to use on an iOS device because that requires an Apple developer account, which we do not have at the moment. But as you can see, everything works as expected, and we will be able to use the physical device for our final demo in 404.
So these are our plans for ECEN 404 and integration individually, what we plan on doing in order to make the integration easier. For my subsystem, I do plan on fulfilling the 3D cases for the entire appliance. So we are planning on manufacturing these, and as a team, we are planning on doing some research and making sure that we choose the best materials and overall manufacturing for the encasings, as well as integration with the control subsystem on PCB. So this is working with Armando to make sure that I have all of the modules necessary in order to control the signals that he will be programming. And then finally, making sure that all of the connection from the hardware elements are made safely and in a compact appliance.
And for the control subsystem, firstly, I do plan on implementing how to receive information accurately from the user input from their mobile device. So this would be like the set time and the set temperature, and just being able to implement those accordingly to the functions they're supposed to have, as well as interfacing the hardware components and implementing the PID control. So this PID control would control the heating element and adjust the power given to it. And I would also have to be able to enable the water pumps. And lastly, I do plan on implementing internal timing as a failsafe from connection issues. So this means the set time, it is going to be on a timer on the mobile device, but it is also going to be counting down from within the microcontroller as well. Just in case there's any Bluetooth connectivity issues, that time will still run effectively.
And in terms of the software subsystem, my plan for ECEN 404 is to implement the BLE connection library and communicate with the microcontroller. So at the moment, I already have all the things stored within my application and all the libraries that are needed to connect to the microprocessor. But that just includes getting all the UIDs and the connection commands integrated, and then running that on Armando's device to ensure that it works with the microprocessor and that the information that is being sent over is valid. Another thing I wanted to implement is the database system to store frequently cooked configurations that the user has, and also to implement an API that will allow the user to have various recipes that they would like to see and use along with their cooking. And finally, I want to be able to polish the interface and design of the mobile application and overall create a cohesive product.
Yeah, and our overall goal for integration is to have a complete working appliance, which will allow for us to cook a dish.
And here is our execution and validation plan update. So as you can see, we have successfully completed all of our goals for this semester, and we are ready to take on a new plan for next semester.
So thank you for watching our demo. Are there any questions?